So far we have discussed many important concepts, right? We have discussed centrality, we have discussed page rank, eigenvector centrality, right, card centrality and so on. So we are almost there. We will discuss a few other measures which are also very important, right? So let's look at the new one, which is called the assortative mixing. So what is assortativeness? So assortativeness is a very important concept in network science. So it basically says that whether same types of users are linked to each other or not. Okay, let's say you have a network of users, right, and you also know the, say, political alignment of users, right. So say pro BJP, anti BJP, pro Congress, anti Congress, and so on and so forth. So in this network, you basically want to understand whether a pro BJP supporter or a pro BJP user is linked to another pro BJP user, or a pro BJP user is linked to an anti Congress user, and so on and so forth. Now this, this political alignment is a feature. It can be any feature. It can be, say, a degree, a simple degree. So you want to understand whether degree 2 nodes are connected, degree 3 nodes are connected to each other or not, degree 4 nodes are connected to each other or not, and so on and so forth, right. So if you think of degree as a property, right, so a network with high assortativity would basically say that nodes with similar degree are connected, meaning that degree 1 nodes are connected to each other, but degree 1 and degree 5 nodes are not connected. Degree 2 nodes are connected to each other, but degree 2 and degree 6 nodes are not connected. So nodes with similar degrees, they are connected, okay. And how do you quantify? It's very simple. You can use a simple Pearson correlation, okay. So what you can do, let us assume that this is a network, and say A, B, C, D, E, right. So let us first arrange all the edges, okay, right. So you have edge AB, you have edge AC, you have edge BC, then CD, then BE, okay. The degree of node A is 2, degree of node B is 3, right, degree of node A is 2, 3, 3, 3, right, this is 3, 1, 3 and 1, okay. So now you have got pairs, so 2, 3, 2, 3, right, 3, 3, 3, 1, 3, 1, okay. So now you can easily calculate Pearson correlation. What is Pearson correlation? Pearson correlation is basically covariance of x comma y by standard deviation of x times standard deviation of y, right. And you have these two variables, this and this. So this is one. So you can think of x. So x has this columns, y is this column. So you can easily compute covariance between x and y. You can also compute standard deviation of this column, standard deviation of this column, and that's all, right. So if nodes have similar degree and they are connected, therefore this would tend to be 1. If dissimilar nodes with different degrees, they are connected, this would be you can think of either assortative or random. If the Pearson correlation tends to be 1, then it is perfectly assortative. If it tends to be 0, then it's basically random, right. And if this is -1, then it is negatively assortative, meaning that node 1 is connected to node 5, say, for example, right. So it is completely disassortative network, right. And this kind of information is very important. For example, in case of link prediction, right, you want to understand whether nodes with similar features, they are connected or not, because that's something which you want to analyze at the beginning, right. If nodes with similar features are connected, then it is easy to predict links, right, because you will say that okay, let's look at x and y have similar features, therefore, but they are not connected, but it is highly likely that they will be connected in the future. Okay. So we always study associativity of a network before analyzing it further. Let's look at the second metric, which is called the transitivity. What is transitivity? Transitivity property says that if A and B are connected and B and C are connected, what's the probability, what's the propensity that A and C will also be connected? A and B are connected, B and C are connected, what is the likelihood then A and C will also be connected? If you recall, this was discussed earlier in the earlier lecture, is something called clustering coefficient, right. So what is clustering coefficient? We have discussed local and global clustering coefficient. Local clustering coefficient will basically, in case of global clustering coefficient, what we have measured the number of triplets, total triplets, and number of closed triplets. So if the number of closed triplets is same as number of triplets, then transitivity would be higher. So this is one triplet, right? And if this edge is also there, then it's a closed triplet. So if the clustering coefficient is high, meaning that indicates that network will have high transitivity value. Okay. Let's move to the next concept, which is called reciprocity. What is reciprocity? So reciprocity says that if edges are reciprocal or not. If there is a connection from A to B, whether B is also connected to A or not. Now this is applicable of course for a directed graph, and if a network has high reciprocity, it basically indicates that it looks like an undirected graph, because an reciprocal edge, two reciprocal such edges would equivalent to an undirected edge, right. How do we quantify this? How do we quantify reciprocity? So reciprocity is total number of reciprocal pairs, right, A to B, B to A, and it is divided by total number of pairs, reciprocal or non-reciprocal, right. Total number of pairs is NC2. Okay, but remember NC2 would not be enough. Why? Because NC2 will also capture such pairs which are not connected. So I am interested in only those pairs which are connected either by unidirectional edge or bidirectional edge, right. So what I am trying to say is that say A, B, C and D, okay. So how many pairs are there? How many reciprocal, non-reciprocal pairs are there? You have AB, you have BD, you have AC, right? But we'll not consider BC because BC is not connected. So I'm trying to understand that if there is a connection from B to C, whether there is a reverse connection from C to B. So the forward connection should exist, right? So I will not consider this pair. I will also not consider AD. Okay. You think of this right here in this example. How many pairs are there? How many valid pairs are there? We have 1, 2, 2, 3 and 1, 3. So the denominator would be 3 and the numerator would be 1 because there is one such pair which which has a reciprocal edge, right? We can also systematically formulate reciprocity. So in this manner. So essentially we are looking at all pairs I comma j, right? And if the adjacency matrix A, if Aij is 1 and Aji is also 1, Aji, then this would contribute to 1. So for all such pairs, I will multiply Aij and Aji. If both of them are 1, then it would be 1, right? It's basically AND operation. Okay, but we also need to normalize it. It would be mod E by 2. Why it is mod E by 2? Because mod E is the total number of edges, and since one reciprocal edge is formed by 2 edges, so mod E by 2 would be the maximum number of reciprocal edges that is possible, right? You can also quantify it in a more sophisticated way. You look at the trace. What is a trace of a matrix? Trace of a matrix is basically the sum of diagonal elements, right, of a matrix, right? So if it is A square, so I have already mentioned in the last lecture that A square would give you the pairs which are connected through 2 hops, right? And we are actually looking at 2 hops from A to B and B to A. So if I start from A and through 2 hops, if I come to A again, right, then it would be basically be a reciprocal edge, right? So if I multiply A with itself, adjacency matrix A with itself, and if I look at the diagonal elements, say 1 1 in this A square matrix, if this is 1, it basically indicates that there is a reciprocal edge. Okay, and the things are same, right? You then divide it by mod E by 2. Take an example. You just take a dummy network and you calculate this quantity and this quantity. You will see that both of them are same. Okay. Now let's look at the other quantity. There is something called structural equivalence. Structural equivalence basically says that whether 2 nodes are equivalent in terms of their neighbors. Let's say you have U and V, right? So if U and V have all common neighbors, then U and V are equivalent, right? So how do we do that? We take the neighborhood intersection of A and B. So NA is the neighbors of A, NB is the neighbors of B, you take the intersection, right? Now this intersection, it may not be enough because it may happen that U has a lot of other neighbors, right? But V has only 3 neighbors. So the intersection will give you 3, right? But U and V are not equivalent because U has a lot of other neighbors also. So we need to normalize it. A simple way to do this thing is that you take something called Jaccard coefficient. What is Jaccard coefficient? In Jaccard coefficient, you take intersection by union, right? Say node U has A, B, C, D, E, F, G, and so node U has A, B, C, D, E, F, and G, these neighbors, and node V has C, D, E. So what's the intersection size of the intersection? Intersection size would be 3. And what's the union size? Union size would be 1. Remember, in a union, it's not a multi-set. In the union, we'll remove the duplicates. So it would be this one. So the intersection, the union would be, the size of the union would be 1, 2, 3, 4, 5, 6, 7. Right? Of course, you can also normalize. So this is just a normalization factor. You can normalize it in other ways. You can actually take the root over, right, square root of the cardinality of both NA and NB. And there are many ways through which you can measure the structural equivalence. Okay. Right. So now let's look at another important concept. This is called degeneracy. Now what is degeneracy? Now this has some relation with the assortativity that I mentioned earlier. So it's basically saying that I'm trying to understand the peripheral structure of a network and the core structure of a network. Okay, what does it mean? So peripheral nodes of a network are basically those nodes which have degree 1. Okay, if you try to visualize it, right, you have fragmented nodes which are orchestrated around the peripheral component of a network. So if you keep on moving towards the center, you will see that you basically you can get core components of a network. So degeneracy structure is explained through something called core periphery analysis. Core periphery analysis, right? Idea is very simple. So let's look at this network. Okay, what you do? You first identify those nodes whose degree is 0. So say these two nodes you see, forget about these lines, okay, these broken lines. Only look at the nodes and links. So this node, right, they have degree 0. You remove them. And those nodes constitute the core 0 set. Now you look at nodes with degree 1. So this node and this node will have degree 1. You remove them. So when you remove this and this, the associated edges will also be removed. That would, after removing this, you will see that some other nodes will have degree 1. For example, if you remove these 3 nodes and edges, this node will also have degree 1. You also remove this node. So you keep on removing nodes with degree 1. First you remove nodes with degree 1, that would result in some other nodes with degree 1, you also remove them. You keep on removing nodes until you see that there is no node with degree 1. Right? So if you remove this node, you will see that you will have only this node, and this node you see that this node will have degree 2. Other nodes will also have degree 2. So these 4 nodes will constitute core 1 set. Now you again keep on removing nodes with degree 2, right? So this node will be removed, this will be removed, this will be removed, and so on, right? That would constitute core 2. Right? And you keep on removing nodes with higher degree, and you will see that after a certain point the network will vanish and stop there. So you have core 0, which is the most peripheral part, then you have core 1, the outermost, the second layer of periphery, core 2, the third layer of periphery, and then say core n, which is the nth layer of periphery, which is the core part of the network. So and then you assign this core value to the nodes. So you say that okay, these 2 nodes have core 0, these 2 nodes have core 1, and so on and so forth. So its core values may not be same as the degree. Let's look at this one, right? Let's look at this one. So what is the core value of this node, the central node, right? The core value of central node is 1. Why? Because although it has lot of degree, right, the central node, but if you remove these 3 nodes, this 5 nodes, the 6 nodes, the 6 peripheral nodes, you will see that this node will become isolated. You will also need to remove that. So degree and coreness may not be correlated. See, they are sometimes correlated, but they may not be correlated. Now think of another network like this. Okay. So when you remove these nodes, you will get core 1, but these nodes, the remaining nodes will have core 3. Core 2 there is nothing. Core 3 you will have all these 4 nodes. Okay. Although degree wise this node has degree 1, 2, 3, 4, but this node has degree 1, 2, 3, 4, 5, 6, but this node has high core value. This is also called k-core decomposition. K-core decomposition, right? K-core decomposition, core periphery analysis, they are kind of synonymous. What basically they are trying to say is that we identify, we keep on removing nodes and try to identify the core part of a network. This core part of a network are the central parts, right? If you want to destabilize a network, you want to break the network, you should attack these core nodes in a network rather than attacking the peripheral nodes. Okay. So, the example that I have given, you see here, this is a core part of a network, and that would basically, you know, give you ideas about the actual bonding in a network. So core parts. So there are studies, in fact in our group we showed that in this fraud kind of network, where you have users, some users are fraud, some users are genuine. These fraud accounts, fraud users are controlled by a very small set of core nodes, and those core nodes are hidden within a network. It's not very easy to detect them, but if you do core periphery analysis, you will see that those nodes are prominent. Those nodes have higher core values. Okay, so that is about the network measure. So in summary, we have understood how to quantify a network, different parts of a network, edges, nodes. We have discussed degree distribution, centrality, page rank, right? Other measures like clustering coefficient, assortativity, reciprocity, degeneracy, and so on and so forth. All right. So I hope you have a fair bit of ideas about network measures. In the next chapter, we will discuss kind of a mathy, more of a math related stuff, which is on network model, right? We will discuss different types of models, which basically will tell you how a network grows over time. Okay, how do we simulate a network? How do we synthetically generate a network? Okay, and so on. With this, I stop here. Thanks.